SwayamPrabha. Digital India. Educated India.
Welcome to the NPTEL online certification course in structural systems in architecture. Today we are in the module 4, the fourth lecture of the module 4, and in continuation this is the lecture number 19. The topic of today's lecture is structural grid and framing. So, in this lecture we will going to have some of the concept which will be discussed thoroughly. One, we will start with the structural grid, and then we will take the load path, then structural configuration, and then the tributary area of the loading and all, and the load distribution. So, in this particular lecture we will have some of the learning objective 2. So, we will configure the structural grid, then outline the load path for a building structure, and we will going to evaluate the beam and column the loading through the tributary area concept. So, the structural grid is one of the important and essential matter in the structural engineering. Even not in structural engineering, it is definitely has a impact on the architectural design also. Whenever a student or maybe any architect, from the student point of view to the master architect, start a particular design, he first has to has a idea of the structural grid, and because the structural grids are the point or the footprint of the structural systems. Basically those are the lines or the points in the particular plan, right, and those lines and points are indicate the structural the systems, or maybe it is columns, or maybe it is beam, or maybe a truss or something like that. So, a series of lines can be created by this kind of a grid. So, those three series of line indicates that in those lines there are structural systems or the element is going to flow or going to be there. And in some of the locations when these two lines are going to intersect, there is a possibility that there is a kind of a vertical members also, which is kind of a column, or maybe there is a linear member also, or a kind of a plate member also, and that may be a shear wall or something like that. So, in between the base of the both the direction it can be created, and this particular arrangement of the base will provide the further classification of the structural grid. So, these are the first, suppose the principal structural points or the footprint of the particular location. So, those are the columns. Now, if I just try to make a kind of a the connectivity between the columns, I need beams, right. So, I need those beam lines or those kind of a grid lines where I may go with a kind of a connectivity or the beam, but this beam will be not maybe in the zone of your in the zone of your the movement, or so it may be above or it may be below. Okay. So, but this column will be definitely going to hamper your circulations and also, that is very much important, that what should be the column grid, the center to center of the columns also, right. And because of this particular lines which is your support or grid, it will give you those kind of a base, that it is a bay length is, this is maybe of 16 feet and that may be of 24 feet or something like that. Okay. So, those are the bay length, and as and when you know this is a bay length or this kind of a the grid is available to you, you can actually can have this major spatial division. So, this is your space availability. So, suppose it is a for a parking, for a kind of a parking. So, can I have one car or can I have two car? You have to actually see from these bay dimensions, right. Suppose this particular area dedicated for a kind of a staircase or maybe some kind of a lift. So, you have to see that this particular bay areas, bay dimensions are fit for that or not. If it is not fitted, you have to increase that one. If you increase, then there will be some changes in the structural geometries or so. Sometimes it may be permitted, sometimes it may not be permitted. Why not permitted? It may create a, because if it is increased, the span is going to increase, that may create a huge bending stress, huge deformations, deflections and all. So, the structural engineer may not allow that one. So, you have to have a tentative idea that what should be the grid size and how that can going to be functional with the your habitat or your the activity. So, now the structural grid, there are different type of structural grid we adopt in our architectural design, and that has to be taken to the structural engineer for their calculations and for their the stability check and all other things. The first one is the rectangular grid, which as it is given, as it is shown in the figure, it is in a rectangle, in a rectangular format. So, the bay dimensions are almost equal or may not be equal, but it is providing this kind of a rectangular the space in between. And there can be curvilinear grid also. Curvilinear grids are in radial fashion. So, the one particular base or the lines, structural grid lines are in radial and another one are in the ring fashions also. So, there can be of different segments. So, it can be given as the angular inclinations and those kind of things in case of the curvilinear grid. There may be a oblique kind of a grid also. So, there are, this is also kind of a merge between the rectangular grid and the curvilinear grid. All are measured in the linearity, not in a curved line, but may be placed in the oblique way. So, there are some typical change of orientations of the column, and finally, there may be a circular grid. So, circular grid is a pattern of the, or it is a the derivative of the curvilinear grid, where it is exactly follow the particular circular curvature. But there are sometimes we may have some kind of hybrid grid, but we have to sometimes go. Suppose the orientation of our building is such a way, there is a circular atrium, but the building is very much perfectly square or rectangular, and there is something projected out which is hexagonal or something like that. So, in the hexagonal part I have to go for the oblique, in the central cutout in the atrium portion I have to go with the circular grid, and then somehow from the circular it will go with some kind of a oblique and then finally go with a rectangular grid. So, it is sometimes happen, you have to create those kind of a the binding from the column, how the column is binding your all the different parts of the building is very much essential. Structural grid, what are the what it is defined or how it is going to define the basic function area of any specific activity is going to define. I have just now told you, because it has some grids. So, suppose this is a particular grid. So, I have some defined area, and in that defined area I have some kind of the different activities. Suppose this is art gallery. So, I have some different, or maybe it is a museum. So, I have something like a circulation zone and some kind of a display zone or something like that. Okay, so maybe there is one end entry, there is another end some kind of a cafeteria, and there is another part, there is a kind of a souvenir shop. So, I have activity zone all around, and because of the requirement of the activity zone I given 3 grids or 3 bays to particular activity, one central bay for some activities or something like that. So, second one, maybe it is a modular relation of any space. Yes, sometimes you can create a modular relation. So, that is the one module. So, I have told you about the suppose something the hostel room, or maybe a hotel room, or maybe kind of a some of the serial apartment, studio apartment kind of a thing. So, you can create a kind of a module and then you can replicate that module one after another. So, that will create a kind of a the modular relations with the space of the grid. Then there is a structural loading intensity. Yes, depending upon the loading intensity you can decrease the grid. Suppose it is very highly intensified loading you are expecting in a particular area, right. Suppose there is a, maybe if I say there is a, in the upper floors you have a library. So, library have lot of load, the live load of in the library is too high because of the books and all. So, if you have clearly indicate that is the library zone, and definitely those the grid size has to be different with respect to suppose a computer lab, or with respect to suppose some other kind of a suppose something a conference room or something like that, where the density of furnitures are less, quite less with compared to the library, or with maybe with compared to some kind of a heavy equipment kind of a storage area. Even we can think of something like a computer lab, and next to the computer lab there is a the UPS stations or those kind of a stations. The UPS stations, if it is a dedicated zone, you have to have there has to be a very intensified loading will be there because of that UPS and all. So, if it is a mega scale, if it is a whole floors is dedicated for the computers and all, so you require a huge space for those kind of a the UPS and all. So, for those area you require a the high that area is coming under the high intensity of the imposed loading or the live load. So, loading intensity is higher. So, you can you have to change your grid pattern, you have to change your dimension or the bay dimensions and all. So, that is another criteria, another way you can define the grid, that intensity of the load. And then there are pattern of spaces. Suppose you have same column configuration, the first one is in the for the ground floor, second floor you have different activities. Definitely you can have the same column layout, column you cannot change because that is already built or already placed in a particular point or the footprint, and you cannot just change it. So, what you can do, you can change the in the internal wall, you can change the particular the infill walls and create a different kind of enclosure to give a different kind of the activity areas, define the different kind of activity areas or so. So, those are the actually the grid defines the your different kind of arrangement, different types of the loading intensity, different type of modular relations and the basic functions of a particular activity area. So, in the load path what we have, you have the multiple type of the load path, and because of this particular the transmission of the particular the load from building superstructure to the substructure, we have different type of load path, and load path is actually what we have to see that load how from one point to the other point, particularly from the superstructure to the foundation, through foundation to the ground, how it is going to channelized. So, there are depending upon that there are two type of load path, one is called the gravity load path and another is called the lateral load path. In the gravity load path, the loads are of gravity, which is your dead load and the live load, which are downward toward the downward to the building from the vertical path. You will take a very vertical path from the top to bottom, and this particular path will actually going to start from the slab and it is moved towards the. So, if I say it is from the gravity load comes toward the floor slab first, and from the floor slab it is going to the beams, and from the beams it goes to the neighborhood columns, and from the columns it will go to the foundation. So, it goes like that. Whereas, in case of a lateral load path, this load path will going to have a different way. So, it is lateral means it is going to hit the building not in gravity way, it is in laterally, that is in the horizontally it will going to hit, and that kind of a load comes when there is a cyclone or there is a very high wind, and of course, there is an earthquake, then that kind of a thing the building oscillate like this. In case of a high wind, the wind flows like that, and that will create a kind of the lateral load on the particular building or particular structure. So, lateral load path always going to that also going to be transferred from the beam column and finally through the soil, through foundations also, but the path is going to be different. It will take a different path. If you see if you follow the arrow, it will take the path like that. Lateral load first come to the either floor slab or in the beam column junction. Whenever it comes in the floor beam column junction, it will take either through the column or through the wall, it takes to the foundation. And if it comes to the floor slab, it is called as a diaphragmic action. Then the diaphragmic action it gives to the beam, the floor the load is transferred to the beam, peripheral beam, and the peripheral beam will transfer that to the column and then finally to the foundation. So, like that this particular path will going to happen. In the structural configuration, you can have different type of structural configuration altogether. The first one, which is very common nowadays or to us, is that the moment resisting frames, that in the last lecture we have discussed, that portal frame, the beam and column, 2 columns and 1 beam, just like a football goal post or maybe a hockey goal post, is the simplest kind of a portal frame or the moment resisting frame. Now, if you just multiply it in the bay and also in the horizontal and in also in the vertical, the whole beam column systems is ready for a particular building to construct. Okay. Of course, there are slabs also in between. So, these beam column systems, when it is comes under the only beam column systems in a monolithic way or maybe in the steel cases also, in the steel as a member of the beam or column, this is altogether is called the moment resisting frames. But this particular frame, this kind of a frame, sometimes not going to be serve the purpose. You may have some different kind of a or high degree of loading, maybe some kind of wind or maybe sometimes some kind of the earthquake, or maybe sometimes because of the different building has a differential height, and because of that there is a differential kind of a load distribution. Okay, in case of a tall buildings or so, in that case we can go with kind of a braced kind of a frame. So, it is same, it is moment resisting frame is all about, but in some of the frames, some of the typical areas or some of the typical bays in strategic locations, we will create a kind of a bracings, and this bracings will give you inherent, it will improve the inherent kind of a strength of the particular frame or the particular moment resistance bracing frames, and then it will give you much more the stiffness or much more rigidity in terms of the lateral load carrying capacity. Sometimes we can go with the shear wall. So, what is a shear wall? It is a wall which is a structural wall which can take lot of amount of shear force. So, sometimes it is required when there is a high rise building or tall building. We will discuss that one in our last lecture or this particular course itself. There are 2 such lecture will be dedicated for that. So, in that shear wall we will put the shear wall in the strategical locations just to encounter the huge shear which can be created by the lateral load, okay, or the wind or earthquake. So, different type of configurations are possible with the different type of structural systems like moment resisting frames, shear wall, bracings and all. Next is the tributary area. In the tributary area is that a particular beam will take load, gravity load, that we have just now discussed as per the load path. Now, this beam will be taking a slab will have 4 beams, right, in the periphery. So, what will be the contribution of the each beams from the slab? That is the, you have to first find out, see the what is the tributary area of the beams, and from the tributary area that we can find out the what is the share of the each beams each beam, how much is the load is going to be shear. So, from that point of view, first we have to see the beam tributary, not the column tributary, because as you see that the load path, the slab, I am talking about the gravity load, the slab, the load comes on the slab, the dead load is itself the weight of the slab and the live load because of the peoples and the furniture load. That load first goes to the slab, and from the slab it goes to the 4 side beam, right. So, first we have to demarcate the how much is the share of each 4 beams, and from that particular share of each 4 beams we now have to calculate that what will be the share of each 4 columns. So, gradually you have to see. So, that is why when we talked about the tributary area, first we have to see, locate a particular typical size of a slab, and from that slab you have to actually break it in different part like a piece of cake. So, this part is yours, that part is yours, like that, right. So, that is the tributary area. So, this tributary area is depend upon the slab aspect ratio. Slab is, suppose for the time being, a slab is a rectangular or maybe a square kind of a slab. So, in that slab the dimensions of 2 sides are L1 and L2. The ratio of L1 and L2 actually create creating that is the key parameter of the tributary area. So, it can have 3 type of the ratios available or ratios possible. One, when the L1 by L2 is greater than 2, when it is in between 1 and 2, and when it is 1. Okay. So, less than 1 is not possible. In case of less than 1, this L2 by L2 is higher, then it is again going to be more than 1 or so, right. So, when it is L1 L1 by L2, I am sorry, this is same, maybe L1 by L2, when it is, or L2 by L1, anything is possible. L1 by L2 is greater than 2, it is a narrow strip like thing, right. It is a very narrow, one side is twice higher than that. So, in that case, what is going to happen now? How much is the tributary area? What is the contribution to beam AB? What is the contribution to beam CD? These two long beams, and there are two short beams AC and BC. What are their contribution? Let us see. So, contribution is like this. The beam AB will have half contribution and beam CD will have another half contribution. The smaller beams AC and BD will not have any contribution. No contribution to the AC and BD, shorter beams. So, both the contributions all will be in the A, B and CD. These are actually came out from a lot of the experimental data and all. So, when it is more than 2, it is narrow strip, the contributions is like that, right. So, B and BD and the AC will not have any contribution. So, 50-50 contribution between the two long sides beam. So, this is the way of it will going to contribute. So, now suppose if I have the some data with me, suppose this is a slab which is having 150 mm thick, and the density of the material, that is concrete, is almost about 25 kilonewton per meter cube, and the thickness of the floor slab is floor finish, of course. Over that there is a top up or the topping this floor finish, which is having 35 mm thick, which is little more than 1 inch, and the density of that floor finish is 16 kilonewton per meter cube, and these two will configure that actually constitute the dead load of the slab, right. These two are the dead load, own weight. And suppose there is a live load intensity of 3 kilonewton per meter cube. 3 kilonewton per meter cube is almost about 300 kg per meter cube. 300 kg per meter cube is 1 meter by 1 meter, 300 kg. Suppose each person is having 50 kg weight, like me, my weight is 60 kg plus. So, something like that, some like me. So, there are almost how many? 300, and there means 6 people are there, 6 people in a 1 meter by 1 meter area. So, that is the intensity of suppose the live load, something like that. If you imagine try to visualize the thing, you visualize like that 1 kilonewton is almost about 100 kg, right. 1 kilonewton is almost about 100 kg. So, 3 kilonewton is 300 kg in a meter square. And I have also given the L2 and L1, L2 is 2.4 meter, L1 is 6 meter. So, that is why the ratio is more than 2, right, and that is why it is a narrow strip. So, if that is so, let us find out what is the contribution of A and B, right. So, then I take a 1 meter width of the slab of this particular yellow kind of a diagram that I made. So, the dimension of this diagram is 1 meter one side, that is the unit width, and this depth is 1.2 meter. Why 1.2 meter? It is half of L2. L2 is 2.4 meter. So, that is 1.2 meter. So, now find out how much is the load of this particular yellow strip, which is 1 meter width and depth is your 1.2 meter. So, I have found out the load of slab per meter is 1. So, first I have found out the volume of this. The volume is 1.2 into 1 into 0.05. Why no 150 mm is the thickness, and I multiplied with the density. So, 4.5 kilonewton is the load per 1 meter of the slab of that particular small strip. So, that is that particular 1 meter of that particular strip, converting that equivalent load of 4.5 kilonewton is applied on one beam. Similarly, I found out the load of this is floor finish, that is 1.2 into 1 into 0.035 into 16. 0.035 is a 35 mm thickness, this remains same. So, floor finish, suppose I assume the floor finish over that, and 16 is the density. So, this much is the 0.672 kilonewton is the amount of the load that on that is due to the floor finish. and if you add this to 4.5 and 0.672, that means 5.172 kilonewton meter is your the load of total dead load. Total dead load is 5.172. Now let us see how much is the total live load. Live load intensity I have told 3 kilonewton per meter square. So how much is the meter square of this yellow area? The yellow area or this 1 meter strip is having area of 1.2 multiplied by 1 meter. So that means 1.2 meter square into 3. So that means 3.6 kilonewton per meter is the total amount of the load of due to the live load, and total dead load is 5.172 kilonewton per meter width or meter run. So total UDL on the beam will be this plus this 5 point something plus 3 point something. So that is 8.772 kilonewton per meter. So I can say the AB or BD whatever both the beams are equally going to carry a UDL of 8.772 kilonewton per meter. So when it is a narrow strip, it's the both the higher length beams in the perimeter will going to take the UDL intensity. Two short side beams 0, they will not going to carry anything. Let us go to the next aspect ratio. Now let us see what will going to happen the column influence. So this column will have this yellow area influence. So the I have already found out the total square meter of this particular load, the square meter load. So that is the 1 into 1 into point. This is the total volume of the concrete slab. This is the volume of my the floor finish, and this is the live load. So 7.13 kilonewton per meter square is the total amount of load per meter square, and I find out the tributary area of each column is half of this and half of other side. So 3.6. So I can directly multiply these two and find out that. So if the rectangular, if it is rectangular kind of a thing, by L1 by L2 is in between 1 and 2, it is rectangular kind of a strip, then the tributary area is like this. So now everybody has some kind of contribution. So these shorter ones are BD and AC will have a triangular contribution, whereas the longer one AB and CD will have a trapezoidal contribution. So to do that, so I have drawn like that, and this is the contribution, and to do that I again take that particular example where now the strip length is going to increase, and this is now if I have taken L equal to 6 and L2 equal to 4 meter to have the ratio within 1 to 2. So this is your strip length 1 meter one side fixed, and other side is half of the L2, that is now L2 is 4 meter. So half of L2 is 2 meter. So I have found out this has to be floor finish. So I have found out instead of earlier it was it was 1.2. So now it is going to be 2. So I have changed those calculative values or also the slab load. So finally the UDL is 14.62 kilonewton. But is it going to be UDL? See, imagine this particular AB is under this trapezium load. So that means if this is A and if this is B, and if you just orient this particular beam vertically above, so the orient this slab, so slab will be resting on the beam like this. So the load will be something like that, right? So if you see, the loading will be the trapezial loading. So in between these 2 points it is 14.62 and then gradually diminishing to 0. Whereas in the, can you tell me what will be the pattern of the loading in shorter side, BD or AC? It will be highest at this particular point and then gradually diminishing. So it will be a triangular kind of a loading, where the apex of the triangle will be the UDL of the 14.62, but gradually it will be diminishing. So it is not only UDL, but uniform varying load is also applicable in the beams in case of the rectangular strip or so. So here In the same problem, I have found out the how much is the contribution to this particular slab, and this particular slab has been contributed almost about 43.86 kilonewton, because this is a tributary area of one slab, 1/4 of that, and that will be going to take care of this intensity of the total load is 7.31 kilonewton per meter square, including the live and dead load. So, in case of the square strip, what is going to happen? If you remember, initially it was flat, two strip of rectangles, and then it is going to be a trapezium and triangle. Now it is going to be a perfect triangle. So, each and everybody will have same amount of load, and this load will be the triangular load. And suppose I have this is the way of the distribution. Suppose the same problem I have, just I now take the L2 as 6 meter. So, the strip length will be 3 meter by 1 meter. 1 meter remains same, because that is the unit load on that particular strip, and this is 3 meter, and this I have calculated, and then I found out that the UDL is your 21.93 kilonewton per meter, and then the distribution of load is a triangular, because all the 4 beams will have the same kind of contribution of triangular kind of a load, and the contribution of the column will be also 1/4. So, I have also calculated the 1/4 calculation. Suppose this is a load distribution for this particular kind of a beam, this particular kind of a grid. So, 3 meter, 2 meter is the grid size and all. So, I have calculated the aspect ratio. If I know the aspect ratio, so I can find out the how it will going to divide, because of the tributary areas from the aspect ratio, and from there I found out this particular load and all the densities and all. So, from this tributary areas and all, I found out that how much is this loading, and then from there I can find out the loading also. So, see, this is 11, this is 11. How I got the 11? Because 7.31 is the intensity of the load, and 1.5 is the depth. This is 1.5 is the this depth, right? Half of this 3. So, I got 11, almost 11, 10.9, like that I got all the depth and all. So, from that point of view, I found out all the loads, and then suppose you take this beam, that beam is A1, this is your A1 and this is your A3. So, this beam if you take, this is 11 and 11. So, this is 11 and 11, there is only one support. If you take suppose this beam, next beam, which is B1, B3, so it actually 11 comes from here and 7.3 comes from here. So, right, and this is 14.6 comes from here and 11 comes from. So, you have to add. So, this is the intermediate beam. So, like that. So, here it is, there is no C1, this is C1, C2, no C3, sorry, C1 and C2. So, like that. So, all the 4 beams has been calculated, and also this beam, that is A1 D1, A1 D1 is this beam, this is A1 and this is D1, which will be supported. There are 4 intermediately 2 supports. So, I have calculated that. See, in this portion there is no load, because that is a small side strips. So, there is no load, only 11 is applicable here. If you take this one, so it is 11, 11 plus 11, 7.3 plus 14.4, I am sorry, it is 14.4, 7.3 goes here. So, this is a shorter side, like that. So, here also if you see 11 and 14.4, because there is no such beam. So, like that you can find out the loads, and also from the column contribution areas also you can mark like that. You can find out the area. Why this is 3? Because this is 1.5 and this is 2 meters. So, this is 3. This is the area, and from the area you can convert with this particular loading how much is the load of the column. How I got this 22? 3 in multiplied by 7 into 3, 122. This 10 multiplied 7.31 is 73. Like that you can convert the load. Okay. So, these are some of the references. The conclusion is that the structural grid is the one of the primary character it is going to holds lot of keys in the stage of the design of the beam also. The proportion of the load in the beams and columns depend upon the slab tributary areas also, and the tributary area is based on the aspect ratio. So, in the homework you have to find out the load contribution of the perimeter beams for this particular grade. Thank you very much.